Hello. So my name is Mark Katakowski. I'm the president and chief science officer of Forever Labs. And like Aubrey to Gray tomorrow, I'm going to give you a little bit of a blockchain break. And I'm going to talk about longevity and longevity medicine. So Forever Labs, we're a longevity company. We've been around for about 2.5 years. We were in the summer batch of Y Combinator. And we're based in Ann Arbor, Michigan. But we're operational about 9 states. We got a few docs out here and a satellite office out here. So I'm here not just to talk about longevity. I've been a crypto enthusiast for a long time. I bought my first Bitcoin sending a $20 bill to Canada in an envelope in like 2012. And I'm also an advisor to My Crypto and the board member. So if you want to talk crypto after, I'm happy to do that. But I want to talk to you about another kind of transformative technology that's going on that's going to change it will change the global economy, but it's going to change the global economy because it's going to change the way that our health, our biology relates to time. That's me at my first birthday. So what we have here is kind of, it's not optimal, but this is the best case scenario we have right now when it comes to aging. This is Prince Philip and Queen Elizabeth, and they have access to some of the best healthcare in the world. They've had a pretty good life, blessed life. They're in their early and mid-90s right now, and compared to most of us in the world, this is about as good as it gets. But unfortunately, about 30 years from now, we don't expect it to be able to take another picture of this happy couple. And that's actually the case for all of us. I don't like to think, but I think that when we're born, it's almost like you're pushed out of an airplane, and we don't have a chute, we don't have wings. It's just the question is how long is the fall, but we know how it ends. And so how does it end? Well, some of us literally do fall, but most of us, when we're young, before our middle age, it's mostly accidents or by our own design or someone else's design that we expire. But once we get to middle age, we start to drop off. We start to die from these things called age-related diseases. And what is an age-related disease? An age-related disease is like heart attack, stroke, dementia, kidney disease, cancer. And these are diseases that occur because you fall apart. We understand it pretty well. What happens is you have dysfunction at the cellular level, which leads to dysfunction at the tissue level, which leads to systemic failure. About 100,000 people every day die of one of these age-related diseases. And interestingly, so age-related disease is kind of new to most humans. Throughout most human history, we were got by death in childbirth or by a contagious disease. But because of modern medicine, because of sterile technique, because of vaccines, we've been able to push most of us to this middle age point where we experience this decline, this falling apart. And here's actually from the US. These are cancer statistics in the US. And if you look, this is age at the bottom, and you can see about 45, there's this uptick, this exponential increase in the risk of cancer. And you see the same kind of thing whether you're looking at heart disease or stroke or dementia. And so really, aging is really a risk factor for age-related disease. That's why they're called age-related disease. And so how are we treating them? Well, right now, we're treating them symptomatically. What we try to do is you have a heart attack, you go to your doctor, they try to unblock the blockage in your heart. They try to restore health. If you got a tumor, they try to get rid of that tumor. What we do is we wait till the symptom arises, and then we try to restore health. But that's changing. That's going to change, and that change is happening right now. We're starting to learn how to interact with our body in a way that we can actually preserve health instead of just restore it. And so we can actually take proactive steps. And for myself, speaking for myself, my own path on this, in 2001, I was a PhD candidate. I was working at Henry Ford Hospital in Detroit, Michigan in the neurology research department. And we were working on a treatment for stroke. We were trying to develop new treatments for stroke. So stroke, if you put all the cancers together, it's the third leading cause of death in the United States. And back in 2001, about 5% of people were getting actually treated for stroke, just even treated. And what that meant is that they would give this clot-busting drug called TPA and you got to get it within 3 hours of having a stroke, or else you just basically have physical therapy left. And now we're up to about 15% triage, but still most people aren't even really treated for their stroke. And so what we were interested in is, you might have heard of these cells, stem cells. I'm sure you've heard of stem cells. Stem cells reside in most of your tissues, And these are cells that can become other cells, but they also promote healing, they reduce inflammation, and they're kind of coordinators of building of tissue and healing of tissue. And so we looked at these stem cells in the bone marrow, and we said, could we use these to help the brain heal after stroke, and we could maybe give people an option. And so we did this in rats and mice, and we actually had quite a bit of success back in the early 2000s. And I'm happy to say that because of that, when we started, there was no clinical trials using these bone mesenchymal stem cells that we're using to treat stroke. And now I think there's 14 registered clinical trials in the world using them to treat humans. 4 of those are in phase 3, which is kind of the last stage before breaking into the clinic. And similar things happen in many age-related diseases using these bone mesenchymal stem cells for the treatment of age-related disease, for their therapeutic potential. But something that we learned and has come out in clinical data as well is that your stem cells decline in number and function with age. The graph here on the, I guess that's your left here, is just looking at circulating stem cells, these endothelial progenitor cells and these hematopoietic stem cells. They're stem cells that build your blood or your vasculature, and they just circulate in your blood, and you can count them, how many you have in your blood. And so there's this study, they looked at how many were in young individuals, how many were old individuals, and you found that they decrease with age. And actually, there's a really interesting study in Italy several years ago where they took octogenarians, people who are 80 years old, and they just counted how many cells they had circulating, these stem cells in their blood. And then 7 years later, they revisited these patients, and they found that the concentration they had circulating when they're 80 was predictive of whether they'd be there 7 years later. So they decrease in number, and that seems to be consequential. Also, here on the right, this graph on the right is just looking at these bone mesenchymal stem cells that we use for the treatment of stroke. Well, they can build bone, and this is looking at their bone building potential with age, and it significantly decreases with donor age, as donor age increases. And this is one more example of that. This is the bone mesenchymal stem cells just in culture growing them. And the top line, this one goes up, is if you take from young donors, children. The bottom line, it's like from 70-year-olds, and you can see after 9 passages, they just fail to grow anymore. So there's this started to really bother me. So we were developing these treatments for stroke, and your own stem cells are far more advantageous to treat you because your immune system won't reject them. But as you get older, you lose these cells that could actually heal your stroke. So that, kind of ate away at me. And that's actually why we founded the company that we founded, Forever Labs, is to solve this problem. And our solution is pretty simple. We just take your stem cells today, and we send them forward in time to treat tomorrow, or several years down the line, or hopefully many years down the line. And luckily, you don't need to modify DeLoreans. All you need to do is use liquid nitrogen to do this. We've been cryopreserving stem cells and all kinds of cells for many decades. And what we call this, when you're taking a young cell and transplanting your older cell, we call that heterochronic transplantation, cold storage for your stem cells. And also bone marrow banking is fun. What we do, we're interested in the bone marrow stem cells, but that's one of the most rich reservoirs of stem cells in the adult body. And it's not so bad. So what you do is you get a local anesthetic, and they actually just use a needle, and you feel some pressure, but because of the anesthetic, you don't feel any pain. You just feel this kind of pressure as they pull it a little bit. It's we need a 1/10 of what you need for a bone marrow donation, so it's not too bad. I've been to hundreds of these collections. I've had it, my wife's had it, my mother. This is our CEO, Steve, right after his. So that's what we do. But that's not really the reason why I created Forever Labs, why I co-founded Forever Labs. So, the stroke is bad. You're going to have a stroke and you try to heal the brain. I got really interested in this idea of, well, there's this correlation between this loss of stem cells and this onset of this age-related diseases. And I asked a question. I wrote a couple grants, one to the National Institute of Aging. This is in 2012, and one to the National Institute of Health. And I said, what if we actually treat this decline in stem cells? What if we actually because you can grow these stem cells. That's one great thing about them. You can take them out of the body, and you can duplicate them and expand them to great numbers. I've done it my own. I got more stem cells, bone marrow stem cells, outside my body than are inside my body. And I said, what if we just treat that loss? And we could take actually young animals that were genetically matched to older animals and treat them with younger animals, younger stem cells. And they said, that's crazy. And they said, no, I didn't get those grants. But there was another group at the University of Texas in Arlington that had a similar idea. They were working at osteoporosis, which is the loss of bone density with age. And they said, well, what if we used young genetically matched stem cells in older animals with that slow osteoporosis? And they used these bone mesenchymal stem cells. And they did this. They transplanted them. And they found, yeah, indeed, it does slow osteoporosis in these animals. But serendipitously, they found that the animals actually live significantly longer as well. And that is, really, about a year after that, there was another group that did similar work, and they had a similar result. They extended those mice by their lifespan by 16%. And 2.5 years now, when we founded Forever Labs, I was just turning 40, and I was having, I guess, a midlife crisis, and I told my co-founder, I was like, I got to bank my stem cells. I want to do this. And we are going to do this in humans. I'm happy to say that we're doing this study in mice right now, a more optimized version of it. I would love to share the results of that, but I can't do that right now. But I can tell you that we've been able to significantly improve upon this. So what's coming is that you're going to have more options to maintain your health. Banking your young biology, I believe, is going to give you a leg up to that. But there are other technologies as well that we're bringing online to practice health maintenance, to maintain biology over time. We're collaborating with some people, and there's others that and we're working on some of our own technologies to this end. It's not going to be easy. Humans are complex. But I want you to know that, like Aubrey said yesterday, this is doable. Aging isn't intrinsic to biology. So we have examples of it. There's the amoeba, single-celled organisms. They don't age. When an amoeba divides, you don't have a young amoeba and an old amoeba. You have two amoebas the same age. They just simply fix the damage faster than it occurs. They just can repair, environmental damage faster than it happens to them. This happens also in multicellular creatures like hydras. Hydras don't experience any increase in mortality over time. They're able to do the same thing. And we are doing this now in larger animals like mice and rats and monkeys, and it's coming. So, restoring health that's lost is good medicine, but if you can prevent the loss of health in the first place, that is the best medicine. I'm sure that my grandchildren are going to look at a picture like this, and they're going to say, why are those people in chairs with wheels, and why is their hair white? We have continued to extend healthy human lifespan with the application of our best medicines. And our medicines are getting better, and we're going to further extend healthy human lifespan. If aging, was something that you could buy, nobody would buy it. Thanks so much for your time. Happy to talk to you off stage.